Hello all, welcome to ML Industry. Today in this video, we will discuss two most common problems in machine learning, underfitting and overfitting. The topic we will discuss are as follows. First, we will see what is underfitting and what is overfitting. Then we will move on to a demo code example to understand both the situations. And finally, we will see how we can deal with such cases. Okay, but before starting, I expect you already have knowledge about bias and variance. If not, I request you to go through my video explaining the same. Now, let's jump into our first case, underfitting. So, underfitting can be defined in a number of ways. I am giving you three descriptions to understand it, and we will see it in our demo also. So, the first definition is underfitting is a situation when the model is too simple to understand training data patterns and relationship. Okay, so basically the model we trained with the training data, it does not recognize the data well. Second definition would be when the model has high bias and low variance, then it is known as underfitting. So if you have already known bias and variance, you'd get the idea. So underfitted model has high bias and low variance. Or in another way, we can say when the model hypothesis about the data distribution is wrong and too simple, then the situation is called underfitting. Okay. So basically what we are trying to say, the model does not explain the data very well because it is too simple to follow the complex pattern of the data. Okay. Now let's see what is overfitting. Overfitting on the other hand is just the opposite of underfitting. When the model is trying to figure out the data relationship in so detail that it fails in predicting unknown data. So if we want to define it, there are three different ways I have put it on. So the first definition is overfitting is a situation when the model gets too complex to understand training data patterns and relationships and eventually fails to perform well on test data. Okay. In another way, we can tell when the model has very high variance and low bias, then it is known as overfitting. Again, the concept of bias and variance is important here. And in another way, we can say when the model hypothesis about the data distribution is too complex to generalize on nuancing data, then the situation is called overfitting. Okay, so the underfitting and overfitting is just the tuning of the model that has gone wrong. Whether the model is too simple to understand the data or the model is too complex to predict unseen data. Okay. Now let's take a sample code and understand the situation well. Okay. So without any further delay, let's move on to our Jupyter notebook. So we are in Jupyter lab. So first we will start with importing some libraries, and we have used NumPy, Matplotlib and few modules from scikit-learn, train test split, linear regression and polynomial features. We will see where we use it. After the importation done, we will generate some data. Here I have used X ranging from -5 to 5, and I have taken 100 data points and reshaped it in one dimensional array. And then I have created y, which is a function of x, that is y equals to x square. And moreover, I have added some random noise with normal distribution having mean as 0 and standard deviation and 5. And the shape of the normal distributed noise is same as the shape of x, that is one dimensional array of size 100. Okay, so that is how y is related to x. And I have used random seed 0 to create the repeatability of x and y without any changes. Okay, so now let's create the data. Okay, once the data is created, let's see how the data is distributed. So this is my data. Here x-axis represents the x and y-axis represents the y, and this is how it is distributed. Okay, now that we have the data in place, let's try to create training and test dataset. For that, we will use train test split, and we will pass the x and y, and we mention that 20% of the data will be test data. So test size equals to 0.2, and we will use something called random state equals to 42, or you can use any number here, which will ensure every time you execute this line, it will create same set of data. Okay, so train test split creates x train, x test, y train, and y test. Okay, so we have 4 set of data, and if random state is mentioned, every time you execute the line, the data will be same. Now I have also plotted the data. So if I execute this piece of code, I will see I have train data in blue dots and test data in orange dots. Okay, now that we have our training and test data, let's try training our first model. So first I will try a simple linear regression, which likely to give me a straight line to describe the relationship of this data. Okay, so I have called the method linear regression in LR, and I have passed x train and y train, which are the training data, into this LR to train the model, and training is done by dot fit method. Okay, so once this line is executed, LR is trained. Okay, so LR is my trained model. Then I will use any data to score through LR. So I have passed training dataset to score, and I have also passed test dataset to score to see what are the scores on this trained model, and I have printed the scores here. Okay, so now let's train the model, execute these lines, and because our dataset is so small of 100 data points, it did the training and scoring instantly, and as you can see the result, the training accuracy is 0.005, that means 5% accuracy, and the test score is minus 0.97. Okay, so that means the model is very bad. Okay, it cannot even generalize the same data it is used to train. So let's see how this model looks like. So here is my model. So this model nowhere actually describing the relationship of the data. So the relationship is a something like U curve, right? And the model is saying like this. So it is generalized the model. The model generalized the data so much that it actually loses the ability to explain the data. So this is what we call a underfitted model. It does not represent the data well. Okay, now that we have known what is a underfitted model, let's try to make it complex so that it can trace the data. For that, we will use polynomial features, because from the visual impression only we can see the relationship is not linear. So we need to have a non-linear curve. That's why we call the polynomial feature. And let's try a higher degree. Let's change it to 20. Okay, so I have now a function poly that has a degree of 20, and then this function I will apply on the training dataset xtrain and test dataset xtest to transform it into a polynomial function. So this two line will transform our actual data into polynomial form, and then we will pass our linear regression model to fit these data points. Okay, so I have created the degree, raised the complexity 20 times, let's say. For example, it is not actually that same equation, but let's, for reference, I am saying the model is 20 times more complex. Okay, and then I am fitting the data into the training data and training sample, and then I'm scoring it with the train data and test data. Same process. Okay, now let's see how this model performs. So as you see, the model is performing quite well on the training data, but it is failing on the test data by a large distance as compared to training data, right? So the gap is huge, almost 40%, right? So it is performing very well on train data but performing bad on test data. That is a classic example of overfitted model. Okay, so now if we reduce the complexity, let's say we reduce it to 15, does it make it any better? So if you see, reducing the complexity from 20 to 15, the training accuracy reduced, also the test accuracy also reduced. So it might seem like reducing the complexity is not the way forward, but let's do another time. Let's just reduce it some more. Okay, and let's see how if it is performing well. Well, now the reduced complexity is actually performing better, in a way that we have compromised some training accuracy. So training accuracy reduced from 84 to 81, but the test accuracy improved significantly. It is almost equal to the training accuracy. But let's try to generalize or reduce the complexity a little more. Let's try degree of 5 and let's see. Okay, so the training accuracy also reduced slightly, but the test score improved, right? Let's try to generalize it a little more. Let's try 3. Okay, now that is another situation. Now the training accuracy is less and test accuracy is more. That means you cannot really rely on this result. You cannot have a model that is performing better in unknown data set rather than the training data set. That means the model is not stable. To have a stable model, you need to have minimum difference between train and test data, but the training score should be greater than test. So it should be nearby, but the training should be higher. Training score should be higher. So degree 3 is not giving me the right output. Let's try to add some complexity, and degree 4 is giving me something that we can rely upon or settle for. So my training score is now 80.8 and test score is now 79.3. So the minimum is so the difference is minimum and it is generalized well. So the test score is high enough. Now we can settle for this data. So this polynomial function or this model, linear regression model. Now let's try to see how these two model looks like. I will also plot the underfitted model. Let's see. So here is the output. So here, this line, as we saw earlier, this is the underfitted model. This green line, which is very curvy one, which has many ripples, this is the overfitted model. So here the degree is 20. So it is unnecessarily going back and forth or creating ripple to fit into the data. That is why it is failing on the test data set. So this is my overfitted model. Okay, maybe I have labeled it wrong. So the green one is the overfitted model. Pardon me. This is a mistake. And this is my good model. Okay, now let's see it again. Yeah, now this is correct. So the green one is the overfitted model and the orange one is the good model. So I hope you have a clear idea what underfitted model and overfitted model is, how it looks like, and what is the tuning we need to do. We need to reduce the complexity, and by reducing the complexity I mean we need to allow some error in the name of bias and reduce the complexity in the name of variance. So tuning the bias and variance, allowing some error, modulating some variance, we can create the model that we can settle for. And here we settled for this model, right? And it looks like this, which fits the data quite well. So I hope with this you have got a general idea of what is a overfitting, what is underfitting, how we can tune the model to get rid of these two problems, and we can implement it through code and we can visualize it right now. Okay, so I hope you have learned the concept. If you like this video, please like, share and subscribe to my channel. I see you in the next video. Till then, bye bye.